Hello, this is Mr. Collier, and today we're doing an introduction to geometric patterning. Let's start off with, well, not geometric pattern, but it's going to be related to some geometric pattern in a second. The number of bacteria in a petri dish, N, grows. There's initially 10 bacteria, and then it is doubling each time, as you can see here, times 2, and then times 2 again. So yeah, we have, the next one's going to be 10 times 2 times 2 times 2 times 2, which is going to give you, this gives you 16 times 10 is 160. And if you jump up to 10 days, we're going to have a 10, and then we're going to multiply by 2 10 times, so you can write like an exponent. Okay, so this is going to get pretty large pretty quickly, so I'm going to use my calculator for that. Okay, so repeated multiplication means an exponent. So when you see repeated multiplication in a pattern, you're going to have an exponent in your rule. Okay, so this is actually 10,240. 10,240. Okay, so for n, this is the rule now, you're going to have n equals, starting value is 10, and you're going to multiply by 2 n times. So it's going to be 10 times 2 to the power of n. So that's your equation or your rule. Test it means you test it for one of the ones that was already given. So 0 to, one of the numbers 0 to 3. So I guess we'll use n equals 2. I'm going to use the rule. N equals 10 times 2 to the power of 2, which equals 40. And this matches the table. So the rule is correct. Okay, and next, how might you justify the formula? So you just can justify it by pointing out aspects of the formula, like the initial amount is 10. And it's 2 because we're doubling each time. Doubling each, what is the context here? Every day. Or maybe we'll say the number of bacteria is doubling. Is doubling each day. Okay, and you can say, maybe you could even explain the n. It's n is doubled n times. Okay, maybe something like that. Okay, example 2 is actually very similar. Let's do it though, it's a little bit different. So for the fourth one, so you can see the investment is tripling each year from year 1 to year 2 to year 3. We have 3 times 3 times 3 times 100 for the next one, and that's 2,700. Okay, but notice you only multiply by 3 times and not 4 times. So it's 1 less than the year number. So when you go to do your rule, the investment, I guess we'll call it I, maybe. I equals, you're going to have the initial value, which is 100, and 3 to the power of n minus 1, because there's always 1 less 3 than the year number. Okay, so it's I equals 100 times 3 to the power of n minus 1. To verify, you have to verify with n equals like 4 or 5. Not one of the ones that's given. So test is with these, and this is verify. Okay, so we can verify with a new one. Let's verify with little n, little n equals 4, maybe. Okay, so then by the rule we have 100 times 3 to the power 4 minus 1, which does equal 2700. This matches the table. So the rule is correct. Okay, so this formula is a bit different than the previous one because in the previous one we were starting at year 0, or our initial value, and here we're starting at year 1. So we're starting, maybe you could say, when starting at n equals 1, the exponent is generally n minus 1. When we're starting at n equals 0, the exponent is n. Okay. Okay, so we'll have to have an n or an n minus 1 to justify the formula works. Let's see, we had I equals 100 times 3 to the power of n minus 1. We can call this the initial investment. Okay, and we could say the tripling continues each year. And then we can perhaps explain the exponent. It's the investment is first tripled at n equals 2. So the exponent is n minus 1. Okay, next let's look at this pattern of increasing squares in the two squares below. Okay, we can see what's happening here. These are midpoints, and this is 3. And we have a square instead of a square, basically. So we're going to show that the diagonal is 3 root 2. The diagonal of the smaller square is 3 root 2. Okay, so let's do that. Maybe we can draw this over here. We've got a right triangle with 3, 3, so we'll call it x. X squared equals 3 squared plus 3 squared. X equals the square root of 18, which is root 9 root 2 and 3 root 2. So we've just shown that it is 3 root 2. So let's take a look at how the pattern continues. When we make a new square, we get a 3 root 2, okay? And then we make this new iteration. We get a square of side length 6, and then we get a 6 root 2, and you can show all these steps with Pythagorean theorem. So if we take a look at what's happening here, you cannot add anything to get from 3 to 3 root 2. So this looks like it could be multiply by root 2. So we'll just check it here. If we've got 3 root 2 times, let me check on the side. If we got 3 root 2 times root 2, it is 3 times, now root 2 times root 2 is just 2, the roots cancel. So it is 6, so it is times root 2. It's times root 2 each time. That means you're going to have an exponential rule. So if I multiply that by root 2, I get a 12, and the next one is 12 root 2. So describing words, the pattern for the side lengths. Okay, they're multiplied by root 2 for each n. Your pattern to complete the next 2 rows, so we have that done. Write down the general rule. Okay, so we're multiplying, well, our initial value is 3, and we're multiplying by root 2 many, many, many times. Oops. Multiplying by root 2 many times. so that's going to be an exponent. Maybe it's n, maybe it's n minus 1. Okay, so we can see when we get to n equals 2, we've just multiplied by root 2 once. So this is going to be the case where it's n minus 1. And you can easily check to see if it works. We're going to test it for n equals 1. Okay, so L equals 3 times root 2, 1 minus 1, and that's 0. Any number to the power of 0 is 1, so this is 3. And this matches the table. So the rule is correct. Okay, and verify. Then we could verify with a new one, stage 5. Okay, n equals 5. We have L equals 3 root 2, 5 minus 1, and that's going to be 3 root 2 to the power of 4. That's root 2 times root 2 times root 2 times root 2. So root 2 times root 2 is 2. So it's the same as 2 squared. Okay, so the whole thing is 12. That matches the table, but we might want to draw the diagram to show it too. Yeah. So you can see here. Yeah, so your new one is going to be times root 2 is going to be 6 root 2 times root 2, which is 12. Okay, so this matches the table diagram. So the rule is correct. Okay, justify rule you can explain here. 3 root 2 n minus 1. So the initial square has length 1. Okay, the length is multiplied by root 2 each time. Okay. And it's n minus 1. So I shouldn't have cramped this in here. N minus 1 since we start with n equals 1 rather than n equals 0. Right? Now the perimeter is just 4 times the lengths from above, right? So it's a very similar pattern. It's also times root 2 each time. Okay, so this time you would get p equals 12 is the initial value times root 2 to the power of n minus 1. And when we go to justify, okay, we could just say that the perimeter equals 4 times the length for a square. And we already have the formula for a square, so we can just substitute in the formula for a square, which was 3 times root 2 to the power of n minus 1, right? Okay, which equals 12 times root 2 to the power of n minus 1. Alright, so that's how you can justify or prove that it's that the perimeter formula is this. Alright. Now the area looks like there's no surds at all. This is doubling each time. Okay, so your rule is going to be A equals the initial value times 2. We're starting with n equals 1, so you're going to have an n minus 1. And when you go to justify, you can say the area equals the length squared, which is the length rule is 3 times root 2 to the power of n minus 1 squared. That means 3 squared times root 2 to the power of n minus 1 squared. Okay, so that means 9 times, and you can swap the n and the m around. So this is like root 2 squared to the power of n minus 1, and root 2 squared is just 2. And that's why it's 9 times 2 to the power of n minus 1, which matches what we did before. Okay, so that's how you can justify that one. You can also prove it. Okay. In the above, we were told to assume that pattern keeps going, multiplying by root 2. It's possible to prove it. Okay, so let's take a look at a square, and let's call this A, or maybe I'll do it the other way around. Hang on. Let me put the square this way. Okay, let's see, that's A, and I want to, let me draw this in blue. Alright, and let's call this, I don't know, B, I guess. Alright, so this is an isosceles triangle. We can say b squared plus b squared equals a squared. Okay, and that is, yeah, 2b squared equals a squared. If you want to find the value of b, we can square root both sides. Okay, and we have root 2b equals a, and b equals a over root 2. The length of the square, though, okay, the length of the square, let's call it L. L equals 2b, which is 2 over root 2a. And that doesn't quite look like our rule from before, but we can just simply multiply the numerator and multiply by root 2 over root 2. And what we get is 2 root 2 over 2a, which is a root 2. So this proves that when you make a new square, you always get a root 2.